Hi and welcome to this presentation on how to model logic for controlling robots. I'm Siddharth, a technical marketing manager at the MathWorks. In this presentation, there are three main points that I want you to walk away with. First, state machines and flowcharts provide a natural representation of logic patterns that are found in robot control applications. Second, simulation and chart animation capabilities in Stateflow make it easy to understand how your logic is behaving. Third, Simulink provides built-in capabilities which makes it simple and straightforward to deploy the logic onto your robot. Let us have a quick look at the example that we'll be building today. So the model contains two main portions, the plant and the controller. The plant represents the physical environment of the robot, so things like motors, actuators, etc. Whereas the controller represents the embedded system. So the controller reads sensor data from the plant and sends commands to the plant. Let's take a quick look at the plant subsystem. It contains blocks to communicate with the hardware when running on a target. Going back to the controller, it has three subsystems. First, signals come in from the sensor. They are processed, and these processed signals are then used to decide the mode of the system. In each mode, we send out some desired signal values to the low-level controller. The low-level controller then sends out commands to the plant based on the difference between the desired and sensor values. So we'll be focusing on the mode logic portion today. This mode logic is built using Stateflow. Let's run the model and see what it does. I will also open the mode logic portion for you. You can notice that initially I am in the calibration mode where I calibrate the tail, it goes down, I calibrate the light, and it's now tracking a line. It's going around the line, and then you're sort of seeing how the model is moving through its states. And after it has tracked its lines, you'll see that it will come to a stop. It will move to the center. And well, after completing all its tasks, it then moves to the center and does a little bit of a victory dance. I'll show you more about that towards the end of the talk though. So let's go back to the model. While we're using a LEGO robot here, the process to develop, deploy applies to other targets like Arduino, Raspberry Pi, BeagleBoard, etc. just as well. So in this example now, we'll add the logic to calibrate the robot sensors and then make it track a line. The first task is to calibrate the robot tail. Let me quickly familiarize you with the robot that we're going to use today. It has a touch sensor at the top that I can press. It has a light sensor at the bottom that it uses to actually track a line. Then it also, towards the back, has a tail that can move up and down. So this is the upmost position, and then we will try to bring its value to a specific value, say pi by 2, below the topmost value, so that the robot can rest on it. Alright, so let's go back to the model now. For this demonstration, I already included blocks to communicate with the hardware in the Simulink editor. So in this subsystem, I have two blocks to communicate with the tail motor and the light sensor, whereas in the other one, I included one block to communicate with the tail motor again. I dragged these blocks from the Simulink block library. So let me go to the library browser and show you those blocks. So I dragged most of the blocks for creating the controllers from the Simulink block library. The blocks for communicating with the LEGO Mindstorms were from the Simulink support package for the LEGO Mindstorms NXT hardware. Now, to add a state machine to this model, go to the Stateflow block library. In this library, you'll find blocks to model both graphical and tabular state machines. So the chart blocks can be used to model state diagrams and flowcharts, whereas the state transition table block can be used to model state machines using a tabular format. Now, truth tables are great for modeling combinatorial logic. So there are two charts in this library, as Stateflow allows the use of either C or MATLAB syntax for specifying the conditions and actions to transition between states. I'll use the MATLAB syntax as it is easier for new users. So drag and drop the chart block into the Simulink editor. Double click on the block and that enters the Stateflow editor. In the Stateflow editor, the palette on the left contains the graphical objects to build state machines. One more thing to note is that to open your state diagrams and have easy access to them along with your Simulink models, right click on the state chart block and open it in a new tab. Now you have access to your Simulink model and your Stateflow diagram through tabs. Right? So let's look at the instructions that we have for the task that we have to perform. The system should wait till the user has pressed the touch sensor. Now let's get into the chart, and we can represent this wait mode using a state. So click on the state object and drag it into the canvas. Change its title to wait. This represents the wait mode of your robot. Now to model when the user presses the touch sensor, the tail should turn up. So represent this turning up mode as another state called move tail up. We have to now model how to grow from the wait to the move tail up state. To do that, we create a transition by clicking on the edge of the wait state and dragging the transition to the edge of the move tail up state. This transition should be taken when the value of touch underscore sensor becomes greater than 0. So this condition for the transition can just be written on the transition itself. Notice that as I click away from my transition, Stateflow automatically surrounds it with square brackets. That's because Stateflow identifies that this is a condition statement and surrounds it with state machine syntax. As we start in the system, we would like to start in the wait state. So you do that by dragging and dropping the default transition object from the graphical palette onto the wait state. So let's go to the robot and let's now try to run this model. So for that, I go to Simulink, Tools menu, Run on Target Hardware, and I run this model. So running the model brings up the symbol wizard. Stateflow essentially parses this state machine and identifies variables that it does not know, then brings up a symbol wizard with a guess on what the scope of that data should be. This data is only being read from, so I'm only reading the value of touch sensor and then comparing it to 0, so it guesses it as an input. I can click OK. Now if I go back to the Simulink level, it has a chart block with an input. So let's connect this with my state diagram, and now let's run the model again. So my robot is first in the wait state, and now as I press the touch sensor, it goes to the move tail up state. Good. So this part works. So the next instruction is to actually move the tail all the way up for the robot. So one way to do that is to move the tail up gradually for a few seconds, and eventually it will just reach and stop at its uppermost position. So set the angular value of the tail position to be less than the current tail position. So I will do that in Stateflow by creating an action where the desired tail position will be less than the current tail position by a certain value. And this action should be performed as long as I'm in the move tail up state. So I use the during keyword to signify that this action should be performed at every time step that this move tail up state is active. Let's run the state machine now. So Stateflow again identifies these two variables, tail position and desired tail position. One is an input, one is an output. Correct. I go up to Simulink, I connect these values, all right, and then run the model again. Okay, the system is in the wait state, and as I press the touch sensor, it goes to the move tail up state and the tail moves all the way up. Good. Now the next task is to lower the value of the tail to pi by 2 below the topmost position. For that, I'll create a new state called move tail down. In this state, to move the tail down, I create an action that will set the desired tail position to be pi by 2 greater than its current position. This action needs to be performed only once, so I mark it using the keyword entry. After moving the tail down, the system should move to another state called done, where I don't need to perform any action. So let's just create transitions between these states. Now let's run the model and see how it behaves. Okay, so the system is waiting. It should go up, but it just seemed to go down and then go to stop. Let's see that again in the animation in Stateflow and see what really happened. So I'll go to Tools menu and run this again. Well, again, so we in the wait state, we press and then we go down again to the move tail up, very quickly to the move tail down, and here we execute this particular action and then go into the done state. So it seems that we're not staying in the move tail up state for too long. So if I look at this transition, I remember that we had wanted to gradually move the tail up for a few seconds, but I see that there is no condition on this transition from move tail up to move tail down. So what happens is it moves up to the system moves into the moves tail up and then directly moves to the next state before the tail has had any time to move up. So essentially what I want is to stop in this particular state for a few seconds. For that I can use the keyword after, take this transition only after 2 seconds. So let's try this logic now. The tail is all the way down, if you notice now. So as I run the model again, it goes to the wait state. I test the sensor, it goes up and then comes down by pi by 2. And now my robot is ready to balance. Great. So to summarize, in the example that we've seen so far, we looked at how to represent a sequence of instructions or modes of a system. We learned how to transition between them, then how to perform actions while in states, while you're in the state at every time step or only once when you enter, and then how to add time-based logic to state machines. To partition the logic in my design around my existing number of states, I can create a parent state called light calibration. As your design gets more complex, of course, I want this to be the first state in my state machine. Now, as your design gets more complex, you would want to hide away logic in the different levels of hierarchy. And you can do that by subcharting a state. So right-click on the parent state, go to Group and Subchart, and click Subchart. You can see that this has hidden away details from your substate. You can resize this. Now, when you double-click on the state, it opens up and shows all the child states of your particular parent state. Let's go back up. And similarly, you can now build other states and logic and put logic within them, but at the same time hide away details from the top level state machine. Now let's go back to our parent model and look through other parts of the logic. So in this state machine, again, we had the tail calibration phase, we had the light calibration phase, and they were both encapsulated within a calibration state. Tail calibration was sort of what we did in our example. You move this tail up at a particular rate, then you move it down. You space your steps out by a few seconds each. Then you get into light calibration, where you press the sensor, then you basically place your robot on the edge of the line where what you would like it to track, and then you, on the entry of a particular state, read the value of the light sensor and save that value to a variable. And that brings you to the end of your light calibration stage. In the next stage, you want to actually move forward. So the first thing that happens within this parent state is this action is performed, which is calculate distance phi. It takes an input of sensors, sends out d and phi as an output. This is actually a Simulink function. So this brings me to another few things that you can do that I'll talk about. First is you can add Simulink functions by clicking and placing them in the Stateflow canvas. So when you double click on this, this opens this Simulink canvas within the Stateflow diagram. So now you can include Simulink functions this way. You can include MATLAB functions. So same way, when you put in MATLAB function and double click on it, that will open up the MATLAB editor for you, in which you can place functions. So all these functions can be placed within the Stateflow editor and then called within your states within its actions or as conditions for transitions. So over here in this particular case, we used calculate distance phi to calculate the distance that the robot has moved, and phi, which is the angle of rotation of the robot, given the sensor values, which are giving the angular position of the wheels of the robot. So once I get into line tracking, it's a simple control algorithm. I first get into waiting, then I move forward. It sets a specific desired speed, and then I rotate. So I set my desired rotation rate based on the value of the light that is being read, if it's above or below what my calibration was for, right? So I stay in this state for about 26 seconds, and then I set my speed, which is my forward motion of the system, to 0, and I set its rotation rate to be 0. Next, I then move to move center. In my move center state, I wait for a second, then I turn left. To turn left, I first save the initial value of my rotation of the robot wheel to a parameter called phi0, or a variable phi0. And then I actually am setting up a desired rotation rate. The desired rotation rate is set to phi by 6, and after it has moved by 90 degrees, the robot, so phi is, as you know, we're calculating how much the robot has moved. It's being calculated every time step. So I see once my actual angle of rotation has become 90 more than what it was earlier, I actually exit the state and take this transition. When I exit the state, I actually set the rotation rate to be 0, which means my robot should not rotate anymore. Same way, when I'm moving forward, my desired speed is initially set to 0.1. I'm moving forward, and my initial position of my robot is set to d0. When my current position becomes a certain distance greater than the initial, then I take the transition and I exit my move forward state. And of course, when I'm exiting, then I use the exit keyword to say that the desired speed should be set to 0. Similarly, going right means that the desired rotation is minus phi by 2. And basically, I then go into the victory dance state. Victory dance is quite similar, just the same few things that we've talked about. It's just a combination of conditions, actions that we've done so far, looked at. So some state actions on entry, then I go into the waiting state. It moves front and back, which is up or down, and it moves between them after some time for a few times, and then it either moves half left, transitions left and right a few times, and then moves half right to face forward again, and then it does the whole operation a couple of more times. So it goes back up to the top. So after it has done all these operations, it goes down and takes a bow. So it does that operation only once, goes basically up once, goes down again, and then goes to the stop. So I'll just run this last portion for you one more time so you can quickly have a look. Now, given our resolution, you won't be able to look at each of the details in all these states, but it'll give you a sense for how the transitions are being taken in the algorithm. So let me actually animate the robot one more time and make it run. And there you can see my robot is happy. It's going through its moves. Yay, 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 yay. And well, anyway. And then it takes a modest bow. It's a meek little robot, so it takes only a modest bow. Thank you. To summarize, the three main points that I talked about today are: first, state machines and flowcharts provide a natural representation of logic patterns found in robot control applications. Second, simulation and chart animation capabilities in Stateflow make it easy to understand how your logic is behaving. Third, Simulink provides built-in capabilities which makes it easy to deploy your software onto low-cost hardware targets like LEGO, Arduino, BeagleBoard, and a few others.